Alright, we've got a really cool pattern today called the sliding window pattern. And the thing about this one is that it is pretty easy to implement, and it's kind of surprisingly simple, but it can be a bit tricky to reason about, to just form a mental model. So I'm going to pitch it in the context of some other videos I've done, namely the multiple pointer patterns. So if you haven't seen any of the videos I've done on multiple pointer patterns for solving algorithms, it might be useful to check out some of those, but you don't need to watch those first. Anyway, what this pattern is good at is subset and subarray problems. So if you see anything that asks for a subset or a subarray, this might be one that you want to keep on your radar, especially if it's consecutive. We'll talk about that. But essentially it takes a problem like that and turns it from its naive approach in quadratic time to linear time solution. And I've got this little box, this little beautiful ASCII art. Probably doesn't make a whole lot of sense right now, but this is going to be our window, and these fun emojis right here, these are pointers that I'm going to use to solve the problem. Not really a pointer problem in the sense that other pointer problems are, because they're fundamentally related to each other. We don't actually need them to solve this problem. We could generate the distance between them, but I think it's a little cleaner if we do it this way. So anyway, just keep that in mind. There are going to be two little pointers, and we're going to slide this box around, and we're going to use it to calculate a sum. And here we go, getting into the problem definition. Write a function called maxConsecutiveSubsetSum. It's definitely a mouthful, but it's precise. That accepts a list of integers and an integer n. So input, we have two parameters. First parameter or argument is going to be a list of integers, and then the second one is going to be an integer n. And we're going to return an integer representing the maximum sum of n consecutive elements in the array. So essentially we have an array like this. We have an array as our first argument, and we have a number as our second. So we're going to chunk the array into little subsets like this, and then sum them and say which one's bigger. So here we're doing 2 at a time, and we're going to say 7 and 9. What's the sum of that? 16. 9 and 20. What's the sum of that? 29. That's bigger than 16. So make 29 our biggest one yet. And then 20 and 4. 24. Not bigger than 29. So we're basically just going to do that. And you can see how a naive solution might take two nested for loops to do this, and just start at one element and count up to n from this element. So it would just count up these two and then iterate and then sum those two and then sum those two and then sum those two. Not a huge deal when your n is 2 and your array is small, but when your array is very big and your n is large, that's a lot of calculating. So say our array was like 6 times a million or whatever, but just visualize it as 6, and then our n is really big. Let's say our array is really big, our n is big. We're going to start at 1, and then we're going to have to sum a whole bunch, and then we're just going to move up one space, and then sum a whole bunch. And so you can see it's a quadratic time problem thinking of it that way. So the sliding window problem is just going to do this neat little trick to do this in linear time. So we looked at some of those cases. Basically, an empty list, we can just return null. Anything less than n, we can just return null. Or any list that has a length less than n will just return null. Even though it says it'll never be smaller, we want to handle the empty case by returning null, so we might as well just handle the others there. We have some test cases. We'll come back to those later. And we're going to start with our function. So maxConsecutiveSubsetSum. Here's our list of integers. We're going to call it list, first argument. Second argument is our integer n, which is the number of items that comprise our subset. And we need to return an integer, the max sum. So, like I said, we're going to start off immediately by just saying, okay, if the length of the list is less than our n, that's, you gave me bad data, that's wrong, return null. We don't need to go any further. And next, we're just going to establish our max sum to be 0. We don't need to, I just have this little note, oh, sorry, that's my screen dimmer, I'm going to turn that off. So this max sum here, we can set it equal to 0 because we are immediately going to establish a baseline max here. So in some problems you might need to set this to a minimum value like -infinity or something, but we don't need to do that here because right away we're just going to loop over our array beginning at 0 and starting and going up to n and calculating the max sum so we have a baseline value. And then we are going to assign 2 pointers. These are little emoji arrows I referred to. We have P1 and P2. The P1 is going to start in the beginning of our array here, and P2 is just going to start at n. So we have this space between these two, and they're always going to move together. So they're just going to be the edges of our window. And then we have our temporary sum, and we're going to set it equal to our max sum. So when we start out, if we look at this, we have an n equals 3, and this is our array. So our max sum is going to be the sum of just these first 3 items, and we calculate that here. So 5 plus 4 is 9, plus 7, 16. And if I make any mistakes in my arithmetic, you're gonna have to forgive me because this, like, one of my biggest fears is math under pressure, and I'm not very good at it. So anyway, temp sum, we're going to assign to our max sum. So these values are the same, 16 and 16. And then we're going to start our logic. So like a lot of these patterns, we handle our edge cases, we assign some variables that we're going to need, and then we run our iterative logic, and then we return our value. So our iterative logic in this case is just going to stop. Our stop condition is when our P2, the leading edge of our window, crosses over the threshold of our list. So we're just going to be sliding down, calculating sums, and figuring out what's big and what's small until we get to the very end there, and then we'll stop because we've calculated everything. So that's our stopping condition. And then we are going to just calculate the sum of each of these. And we have one to begin with. So this is kind of the meat right here. This is the logic. And this is what's really simple about it, because you don't even need these P1 and P2 variables, because you could generate P1. You could technically use a for loop and just iterate over this stuff and then say, for index I, subtract n, and then you would get this P1. But I think it's more readable if we just use this P1. So let's just keep that there and think about it in this way for now. And what we're going to say is our temp sum equals our previous temp sum, which in this case was initialized at that first sum, that first n sum. And then we're just going to minus what's at P, which is in this case 4. So we're going to minus 4. And then we are going to add the leading edge of our window, 9. So add 9. And this is essentially just saying, like, okay, this edge of our window we want to exclude, and we want to include this edge of our window, because we're always going to have these 3 values. We already have the sum of those 3. So if we subtract 4 and we add 9, we have the sum of the next. And that's really all this is. That's all the logic behind this. So 16 minus 4 is 12, plus 9 is 21. So we have our 21 value there. And then we're going to say, well, if 21 is bigger than 16, I should update this. If 21 is bigger than 16, which it's not, update it. Otherwise, increment our window. Just slide it along. And if we were using a for loop, this would just be like, okay, well, go to the next iteration. So I was 0, now I is 1. And we would just calculate our P1 by saying I minus the number. But we would start I would be this one. We would start I to begin with. We would start I at n and then subtract n to get our trailing edge. But for now, all we have to do is just increment P1 and increment P2 in this case, and we're just sliding our window along. And then we go to this next condition, and P2 is clearly not less than the length of the list, so we're just going to calculate the next. We have our temp sum, and we're going to say 21 minus our trailing edge, which is 5, plus this new value of 20 here. So we have 21 minus 5, which is 16 plus 20, 36. All right, got that one. 36. So our temp sum is 36. And then, then we're just going to go down here and we're going to say, well, is 36 bigger than 16? Sure is. Update this one as well. And then slide our window. So we're just going to keep sliding our window. Now we have 36. We're going to say 36 minus 7 because that's our value at P1 plus our new value. Let's do one little more. Our new value of 4 plus 4. 36 minus 7, 29 plus 4, 33. So then we're going to say our temp sum is 33. If 33 is bigger than 36, return that, which it's not. So we'll just leave that alone. We'll increment this. And we're going to just do that until we get to the edge here. And when it goes over, we'll have the sum of those three, and then we'll know not to do it again. And we'll return whatever our max sum is at that point. And that's it. I mean, that's the sliding window problem. I mentioned how you could kind of do it without these, but you don't have to. You're essentially just creating a little box, and you're turning what would be a quadratic time problem, into a linear problem. I think it's actually kind of a really neat little solution. So anyway, that's all there is here. Oh, I suppose we should run our test cases at the very least. Geez, I can't get up there. Let's see. All right, so we're going to say run test cases here. And there we go. True, true, true. Feel free to play with this. Try to break it. Questions, comments, concerns, criticisms, anything like that, let me know in the comments. And as always, thanks for watching.